All right, everybody. Welcome to lecture 5. We are talking about chi-square hypothesis testing. So thus far, lectures 1 to 4 have only dealt with descriptive statistics. Today, we are introducing inferential statistics. And what does that mean? Well, let's click. So inferential statistics is what we're doing today with chi-square testing. Everything we've learned thus far has to do with descriptive sample statistics and not the population. This week we will learn one technique of several that allows researchers to draw inferences about a population. So this method is called the chi-square test. Chi, not chi, not chai, but chi. So we're going to be looking at chi-square testing. Chi-square tests are used on categorical variables only. In other words, nominal, ordinal, what else? Hopefully you're saying dummy. Yes, nominal, ordinal, dummy variables are all categorical variables. And just like we used contingency tables for only categorical variables, we're going to go back to that lecture and extract those contingency tables that are talking about the sample, and now we're going to be able to use it to talk about the population through chi-square testing. So statistics has F-test, the Z-test, the T-test, which we'll look at in regressions after the midterm. But today we're looking at the chi-square test, okay? So chi-square test and all inferential testing allows us to draw inferences from a random sample to a population. So most researchers deal with samples, obviously not an entire population unless the population is a small, reachable group. And so that's why we see the what's it called? The census in most countries done every 10 years, right? Not every year, because that's not a small reachable group that you can just do it at, whenever you just so choose to do it. The population, so again, we've been talking about descriptive statistics. What's the mean, median, and mode of this variable? What type of variable is? How many variables are there? What are the values for the variable? What's the relationship with this variable and that variable, looking at a contingency table? What's the relationship with this variable and that variable, looking at a scatter plot or a correlation matrix, or correlation coefficient, right? But today we're going to go beyond what we're seeing in the sample, and we're going to try to test to see whether what we're seeing in the sample exists in the population. Can we generalize to the population? Okay, so your estimate of the population is only as good as your sampling design, how you went about collecting the data in a statistically and methodologically sound way. You learn about this in PUAD629 in a different class. Because there's a lot that goes into it, and it's in this class, right? We only look at now that we've collected the data in a statistically and a methodologically sound manner, how do we analyze it, right? But in a program evaluation and program design class, right, we learn how to collect that data so that it is randomly selected, so that it is normally distributed, so that we can actually, so that it is representative of our population. Because a sample is an estimate, and the bigger the sample, obviously, the better the estimate. The bigger your sample of a population, if you get 50% of the population, you have a better estimate of the population than if you get 25% of the population, right? If you get 100 people, you might not have the best sample compared to a sample of 1,000 people, right? So that's what that last bullet is essentially telling us. And so this picture here, we can see that a sample, again, is a small subset of a population. For example, population might be we want to do a study of all college students in Maryland, but then we sample only UB students. Might not be the best sample because it might not be representative of the population of all college students in Maryland. But again, that's not for this course. So for this course, we take it as is and we say, okay, they may have already collected the data in a statistically and methodologically sound manner. So we're taking their sample and we're going to run it and try to make generalizations about the population. Okay, we do the same thing, maybe say for an election, understanding presidential election voters, but then we only look at the Southeast. So maybe we're concerned about what's happening in the Southeast, right? And even then we might not collect the data for everybody in the Southeast. We take a sample from the Southeast. All right, again, sample population. The set of all individuals for whom you would ideally like to have, but which we cannot usually access, right? A parameter, when you hear the word parameter, that tends to mean characteristic that's describing a population. And some reasons, right, why we probably cannot collect population data often or ever is because one, obviously time, two, capacity. Do we have enough people to help us collect this data? What's your research team look like, right? Three, money. If you have a research team that's that massive, you have to pay somebody, right? And so time, resources, capacity, all that is important. And so that's why when we do statistics, we are usually looking at a sample, a subset of the population chosen in a scientifically random manner. If the sample is chosen randomly, it is probably similar to the population. Again, not necessarily something we get into in this course, but just to step back a little and look at what we talked about with standard deviation. If you remember that normal curve, that normal distribution, right? And most things fell in that big hump area and then things dispersed further out. That's normally distributed. And that's what we're expecting to see from a random sample. That things fall, kind of wither at the sides and everybody sort of is, the majority of people are thinking sort of in the same manner. Statistic is anytime you hear the word statistics, a statistic, it's representative of a sample. Just like parameter, when you hear that word, that means a population. A statistic is a number describing a sample. So for ChiSquare Test, the question that we ask is, does the sample provide convincing evidence that the two variables that we're looking at, say gender and salary, right, or age and pay grade, whether those two variables are related not just in the sample, but also in the population as a whole, whatever population that we extracted that sample from, okay? It might be all high school dropouts. It might be all college educated people, right? But that is the population, right? We're not just gonna say all people if we don't mean all people and then we collect data for only high school dropouts. So some of the logic, a lot of this might go right over your head, but these slides are here for your reference, for your benefit to come back and look at it after we've talked about it. In the future slides, you're gonna understand it better, and then these words are gonna make sense right afterwards. We want to test what the relationships that we see in the sample exist in the population, right? Because yes, it's important to know, right, what's happening in this particular sample, but we're not just running a study because of this group of people. We're running it to be able to make generalizations about a population, to be able to say, okay, this is the policy that we need to put in place, right? Or this is what's happening in healthcare. This is what's happening with after-school programs. And so in Maryland or in various parts of Maryland, so maybe we need to provide more funding in all parts of Maryland or in these certain parts of Maryland, right? So it's not a study of a sample in and of itself. It's a study in order to be able to say something about the population. All right, I rest my case. Researchers can develop two types of hypotheses. The first is called the null hypothesis, or H naught. The null hypothesis means that we believe that there is no relationship between variable A and variable B. The research hypothesis, right, would mean that there is a relationship. We believe there is a relationship between variable A and variable B, right? By virtue of deciding to conduct the study, you will always have a research hypothesis, an educated guess about how study variables might be related to one another. Most studies, you're not going to see anywhere where it says my null hypothesis is. There's really not a such thing. This is a theoretical sentence that your null hypothesis is this, right? And it's a statistical term, if you will. Just it's statistical jargon, and we'll learn why we say that towards the latter part of this lecture. So, for example, hypothesis one might be, I believe there's a relationship between gender and salary. Hypothesis two might be, I think there's a relationship between age and salary. Three might be, I think there's a relationship between education and salary. And so your null hypothesis for all of them, H naught for hypothesis one, H naught for hypothesis two, H naught for hypothesis three, all would be there is no relationship between age and salary, gender and salary, education and salary, right? H naught, it's not something that we ever actually write in a study. We just know it intuitively. Because null means no, zero, void, right? Null and void. And in research hypothesis, we're expecting to see something. All right, so is there a significant difference between the expected frequencies and the observed frequencies in one or more categories? This is the logic behind the ChiSquare test. Is there a significant difference between what we see and what we expected to see? Said another way, does the number of individuals that fall in each category significantly differ from the number that we would have expected? Again, is what we're seeing what we would have expected to see based on proportions? So if so, is this difference between the expected and observed due to sampling variation? Something might have happened, right? This sample might be different from that sample because, well, maybe in rural Georgia, things, you know, we collected this data in rural Georgia, we collected this data in metropolitan Atlanta, right? Or is it a real difference? Is there a real difference, right? So are the differences, again, said another way, are the differences in sample proportions likely to have occurred just by chance because of the random sampling, or is that what might actually exist in the population? Again, we come back to these slides 5 and 6. Once we've moved on and understood the calculations of it, these words will make sense. All right, so now let's do the calculations of it, because this is probably the easiest part of all of it, I promise you. So to run a chi-square test, there are 3 steps. The first step is that we calculate the expected frequencies, right? We have what we observed, the sample, we collected the data, this is what we have, right? And then we calculate the expected frequencies based on the row totals and the column totals and n, which we know is the total, the sample size, right? Based on those totals, what would have been the ideal or what would have been the proportional, what's the word? The proportional distribution of these numbers that we currently see in our contingency table. What would have been the proportional distribution of it? We take that expected frequency, we plug it in, calculate our p-value, and then we interpret our p-value. We use that p-value to make an inference about the population. So let me step back a bit. P-value means probability of error, okay? And so just remember that as we're talking. P-value means probability of error. All right, so as we run chi-square test, here we go. So first off, what do we see here? Hopefully this looks very familiar to you, and this you would call a contingency table, right? So a contingency table, what are our two variables here? The first variable I see in the independent variable is gender, male and female. The second variable that I see here is one's opinion about the death penalty, right? Favor or oppose, those are the values for it, okay? So this is a contingency table. We can see that 309 men favored, 348 females favored, right? The total of people who favored, 657. How many people are female in this sample? 519. How many people are total are in this sample? 918, right? So let's, now that we understand the content, what we're using to calculate our expected frequencies, because we're very familiar with contingency tables now, lecture 3, we can now calculate. So the first thing we're going to do is familiarize ourselves with this equation. It's very basic. It's nothing tricky about it. Row total, column total, total sample size, total, as we've been calling it. So row total, for the first row, what would it be? 657. Row total for the second row, what would it be? 261. What's our first column total? Hopefully you're saying 399. Our second column total, hopefully you're seeing that it's 519. And then the total sample size, our N, our total number of observations, is 918. All right, so we have that. Now we can go in and calculate what our expected observations, our expected frequencies would have been for a male who favored, a female who favored, based on the proportions from our row and column totals, okay? So first one, the expected frequency for that 309, we can see our 309, the expected frequency would have been the total at the end of the row times the total at the end of the column times Rn, right? We see that 357 times 399 divided by 918. Boom, just that simple. So what is it saying? We had a sample size that showed 309 males favored, but if we had broken that up just by the row and column percentages and the total number of observations, that number should be closer to 286 people, not 309. Okay, that's what it's meaning. Okay, so we're trying to find out what would these numbers, these four numbers, be if it wasn't by chance, if we were to just break it up proportionally, right? Okay, so we say 286 because we don't believe in a fraction of a person, so 286 is what we're going to call that. So for the next one, we're looking at, the first one was column 1, row 1. So this is the first column, and it was also the first row. Now we're going to column 2 of that first row. So column 2 has a row total, should be the same, 657. A column total for a female, 519. It's different from the male, right? Divided by 918. So we're going to round that to 371. We don't believe in fractions of people, right? And so we're just going to round down because that's where that rounding is taking us. 0.44 takes us down. All right, so let's continue. Expected frequency point of column 1, row 2. Column 1, row 2. Column 1, row 2 has a row total of 261, column total of 399 times our 918. That has not changed, won't change, right? Unless we have a different sample. And then the final one, column 2, row 2. 261 times 519 divided by 918. So we have 148 people. So step 1, it's pretty simple, right? I mean, it's pretty straightforward, I should say. Pretty straightforward. Just looking at the equation, understanding what we're going to do. Row total times column total divided by total for all of our values. For a male that favors, a male that opposes. A female that favors, a female that opposes. Are we concerned with the totals? No, because that's actually our equation, right? So we're only concerned with making expected frequencies for observed frequencies that actually mean something, right? All right, so now we've taken what we just did, moving it into Excel. Well, we've already hypothetically done this in Excel, right? So we didn't necessarily have to pull out a calculator and do it. We did it on Excel. So step 2 tells us to calculate the p-value. This is when things are just smooth sailing because we've done the work, right? We see the work has been done and Excel provides it for us. And now we just plug and chug. Just like in lecture 2 in Excel, we wanted the mean of something. We typed equals, average, and we selected the column we wanted to take the average of. We wanted the minimum. We typed equal, minimum. We selected everything we wanted in that variable to find the minimum, right? Equal, first quartile equals standard deviation. So in the very same way, because we're using the very same software, we're going to type equal chi-square test. And we're going to make sure that it says chi-square.test because there's lots of chi-square formulas, but the one that we want in order to get to our p-value is chi-square.test. Okay, when we type that in, it's going to ask us, just like it does with everything else, hey, what's our actual? It's going to prompt you, right? Just like it does with everything else. So what's our actual? Our actual is the 4 that we already knew existed, right? This is based on our sample, right? 309 people were males that favored, remember? Okay, and our expected is what we calculated already. Right here at the bottom, we calculated it, and here it is in the table. So one thing that you need to know is that 309 plus 348 equals 657, yes? Okay, 286 plus 371 also equals 657. Okay, same with our next row, right? Same with our columns. So what you should be observing here is that we used these row totals to calculate our expected, row, and we use all of these totals, right, to calculate our expected frequencies, but those row and column and total totals are not changing. They're not changing. This is all about proportion, right? We're just creating proportions, cutting it the way that it would have been if there was nothing, no relationship, okay? So now that we've done that, we take chi-squared, and you'll do this in your homework 5. You take chi-squared, it says actual, so you select actual, right? You just select all 4 of these in one click. You press comma, you select expected in one click, you press enter. Now we've calculated our p-value. Just like correlation coefficient, we don't actually have the math behind it. We don't do that in this course because this is not a calculus course, and I'm not going to require you to do that because you guys are here to be public administrators, public analysts, public program analysts, policy analysts, right? So this is not necessarily something, the math behind it is not important. Just know that it is sound, right? And that it's been tried and true. And you literally just have to just understand it and interpret it correctly. So let's interpret it correctly. That's where step 3 comes in. So we've got decision rules. You know, I never leave you hanging because I gotta make it very, very plain so that you understand the interpretation part, because like I said, that is the most important thing. We can calculate all the numbers we want in the world. I can teach you how to do that with your eyes closed. right? But if you cannot step out of this classroom and explain that number to somebody, then that number means absolutely nothing. Then you have absolutely knowledge does not equal power for you because you can't interpret it. You cannot hold a conversation around it. So that's what we're going to get to. We're going to be able to do that in this course. Okay? So we have calculated chi-square, our p-value, through the chi-square test. And now we're going to come up with what we're going to say about the sample. Okay? What are we going to say about about the population? So we're going to make our inference. There are two decisions, just two. The first decision we're going to make is, two options. The first is that we tentatively accept the null hypothesis, H naught. We tentatively accept H naught, which means, what does it mean when you're accepting the null hypothesis? Well, you're accepting in the null hypothesis that there's no relationship. So you're accepting that there's no relationship between these two variables. You're accepting that there's no relationship between these two variables, right? And when do you do that? When the p-value that you just pressed enter and calculated is greater than 0.05. Okay, lots to talk about here. So we're going to take it a step at a time. So the p-value, remember, is the probability of error. In this course, we're going to agree that 95% confidence or 5% level of error is acceptable. Anything higher than that, we can't accept it. We are not willing to accept anything higher than a 5% level of error, a 5% significance level, a p-value of 0.05 significance. Replay that if you need to. All of those things mean the exact same thing. So be prepared to hear it in a lot of different ways. P-value of 0.05 is a significance level of 0.05. A significance level of 0.05 is a probability of error of 5%. Probability of error of 5% means a confidence. You're confident 95%, right? So when your calculated p-value is greater than what we're willing to accept, we're willing to only accept 5% error. Anything higher than that, we're not comfortable with that. In some disciplines, it's much higher than that. In some disciplines, they say, you know what, 90% confidence is okay. So a p-value of 0.1, I'll accept it because I really want to talk about the sample as it relates to the population. Granted, 10% level of error, that's a pretty large percent of error, but you get to like some of this is a soft science, if you will, social science versus a hard science, as they call it. There in engineering and so on, you might want to be 99% confident, right? Because you don't want to be 90% confident that this bridge is not going to collapse, that this road is not going to cave in. We need a little bit more confidence than that. A little bit more confidence than that. And so so in those types of fields, 99%, 99.9%, those are the significance levels or the confidence levels that they're willing to accept. In social science, it's not a do or die. It's not a do or die. No one's going to die that we've gotten their opinion wrong, right? So 95% confidence is what we're willing to accept. This means that this sample has an error level that is higher than that 5% error that we're willing to accept, right? P-value is greater than 0.05, so we're higher than what we're willing to accept. So for example, if the calculated p-value is 0.09, this means there is a 9% probability of being wrong. That the relationship that we see in the sample might not actually represent the population, right? So, or said another way, that there's a 91% chance of being right, that the relationship we see in this sample is generalizable to the population, is statistically significant. That's another term we say. Statistically significant. Statistical significance. If something is statistically significant, that then we want to be able to, then we are able to generalize from the sample to the population, right? And we're able to say that what we're seeing in the sample exists in the population. In this scenario, we can't say that because our p-value is higher than what we're willing to accept error level, right? So since we want to be 95% confident, being 91% confident in the sample generalizes, being 91% confident in the sample's generalizability, not good enough. Because we cannot be 95% confident that there is a relationship in the population, we tentatively accept the null. We tentatively accept that there is no relationship between this variable and that variable in the population. Okay? We can't be 95% confident. In this example, we're only 91% confident. We're saying, so let's just go ahead and just say we can't generalize to the population, right? And specifically, I mean, we're even saying that we're just going to assume that there is no relationship in the population because we have to tentatively accept the null. Statistically, we have to accept the null, that there is no relationship. Option number 2. So option number 1, we tentatively accepted the null because P was greater than the error level that we were willing to accept. Now we're rejecting the null because P is within that area that we're willing to accept. It's less than 0.05, or it might be 0.05 on the dot, but hey, 5% confidence, we're willing to accept that, right? Anything higher? No. But we're willing to accept 5% confidence. So what does that mean? Well, the p-value that we calculated, right? We just press enter, boom, we got our p-value. It's telling us, oh, it's say 0.03, right? Now the p-value is 0.03. Is that less than 0.05? Yes, absolutely. And so that means that our error level meets our standard of being less than or equal to 5%. Okay, percent error. Less than or equal to 5% error. It's at 3%, right? So we have a 3% chance of being wrong. We're accepting the research hypothesis now, right? We're rejecting the null. So what are we doing? We're accepting the research hypothesis. But again, folks, research lingo, right? Statistics lingo. We go with the reject and accept null. We never talk about the research hypothesis per se when we're doing accept and reject. We talk about it later, right, when we start talking in terms of the population. And you'll see that in the next couple bullets. So we have our 3% chance of error that, you know, we're rejecting the null and we're saying, hey, there is a relationship, right? That what we're seeing in the sample does exist in the population. We're saying this with 97% confidence. We're saying this with 3% unconfidence, right? 3% chance that we could be wrong, but 97% chance that, hey, we could be right. We could be right. So using the above p equals 0.03 example, since we are at least 95% confident, actually 97% confident, we're happy about that. This means that the relationship that we see between variable A, variable B, these two categorical variables in the sample exists in the population. This is a statistically significant relationship. This is a statistically significant relationship between variable A and variable B. So what we are seeing in the sample, we can generalize to the population, okay? So what this further means is that, yes, we said it already because we're rejecting the null, which means that that there is no relationship, right? We're rejecting the null, therefore we are accepting that there is a relationship, right? All right. So let's do an example. So, oh, I just, okay. So this example is an SPSS output. It's the same example that we looked at before, actually, but this time I didn't remove our column percentages and our total percentages. So my bad, folks. I apologize. But listen, that's not going to make us stumble because we know what a contingency table looks like. We know what our relative frequencies are because they're percentages, and we know what our absolute frequencies are because they're the basic numbers, the counts. And it's those counts that we need in order to calculate our p-value, right? So we used our counts, 3657 times 399 divided by 918, right? So that's not throwing us off. We did all that. We typed equals chi-square test. We selected our actual comma. We selected our expected that we just calculated. We pressed enter, and here's the number that we got, a p-value of 0.001. So let's make some inferences. The first thing that we should be able to see is that this number is much lower than 0.05, that threshold that we used to make our decision, right? So 0.01 is less than 0.05. So what do, right? Let's just go back one. 0.01 actually is less than 0.05. So what do? We reject. We reject. So here we go. We're rejecting. The p-value means that we can be 99.9% confident that this sample's relationship between gender and death penalty opinion likely exists in the population. Yay! Okay, or not yay, depending on what it was you were trying to prove, right? But that's what it means. So I skipped some steps here, and I want to verbally state them. The first thing that we do, right, we noticed the p-value, whether it's higher or lower, right? So the second thing, so from that observation, we are able to say accept or reject. What's your decision? Our decision here was we reject the null, right? That's the first thing we say. Please bear in mind, this is what you're going to need to say in your practice, in your homework, in your quizzes, in your midterm, and in your final. So please listen. You accept or reject. That's the first thing you do. In this case, we rejected the null. The second thing we do is why? Why did we do that, right? We did that because P is within our, it's less than 0.05. Just that simple. Reject the null because P is less than 0.05. The next thing we do is why. What does that actually mean? We just did the why because it is less than 0.01. So what does that mean? Well, that means that we're at least 99.9% confident that what we're seeing in the sample exists in the population, right? And then 3, that was 2. And then that was 3. Okay, so I said all of it. I'm going to say it again. I apologize. So 1 is the why. We reject because P is less than 0.05. 2, what does that mean? It means that we can, when we reject the null, it means that we accept that there is a relationship, right? We're accepting that there is a relationship between gender and death penalty opinion. And then 3, what does that mean to the population? We are talking about inferential statistics, meaning, just like we saw in the very first couple slides, that we're going beyond the sample to now the population, right? So any answer that you ever give for a p-value must always have the word population somewhere. If it doesn't, I don't know what you're talking about, and I'm just going to mark it wrong. Okay? P-value has to do, inferential statistics have to do with the population. So that's why it's underlined here, right? So 1, we reject because P is less than 0.05, right? We can be at least 99.9% confident, not just 95 even, right? 2, what does it mean? It means that as we rejecting the null means that we accept the research hypothesis, that there is a relationship between variable A and variable B. And therefore, we can say that what we're seeing in this sample likely exists in the population. Okay, I've said it 3 times now, so hopefully one of those stuck. So what exactly are we seeing in the sample, right? Then we look at the sample. This is an example from lecture 3, I believe, when we were introduced to contingency tables. What are we seeing, right? We're seeing that men and women both favor the death penalty more than they oppose, right? But that men are more likely to favor that death penalty than women in the population. That's exactly what we're seeing. We're seeing that men favor more than they oppose. We're seeing that women favor more than they oppose, right? 77% favor, 22% oppose. 67% favor, 33% oppose, right? That's what we're seeing. They favor more than they oppose. But what this p-value is telling us is that what we're seeing, that men favor more than women, that we'll probably see in the population as well. They both favor, but men seem to favor more than females. In the population, that number might not be 77% to 67%. It could be 83% to 67. It could be 93% to 80%, right? It doesn't have to be 77 and 67. That's in this sample. But this sample is allowing us to generalize to the population that shows us that that might look like this: men and women favoring more than they oppose, but men still favoring more than women. That's a lot. So replay this if you have to. And I think it'll make sense. No, it will make sense. All right, so some summary points. The ChiSquare test measures how far the sample is from what we expect to see in a random sample from a population with no relationships. So we did that by our first step, where we understood what our actual frequencies were, right? Then we calculated our expected frequencies based on proportions, what it should look like if, as this says, there are no relationships, right? Then we compared the expected to the actual by doing equals chi-square test, right? We selected our actual, our calculated expected, we pressed enter. Now we have a p-value, and based on our significance level that we've chosen 0.05, we make our decisions, right? If it's greater than 0.05, sorry, can't take it. We have to tentatively accept the null hypothesis, right? There's no relationship. If it's less than our 0.05, whew, that's awesome, because that level of error is within what we're willing to manage, right? And then we can say, yes, what we're seeing in the sample probably exists in the population, okay? So, final thoughts, right? We introduced hypothesis testing here, okay? And we're going to look at an example of how to do that when you're doing your research papers, okay? Or when you're reading a research paper. So for example, we have 3 variables that we want to test. We want to look at gender, the 2 values for gender, male and female. We want to look at education. We've also made it a dichotomous variable, apparently. Instead of an ordinal or interval, we made it, it is an ordinal, but we made it also dichotomous, a dummy variable, where it's just everybody that has high school diploma or less, and everybody that's got college degree or less, or more, or more. So we've broken the groups into 2 only, right? And then death penalty, another dummy variable. We could have made it 3. We could have included the people who weren't sure. So the favor, the opposed, and the people who weren't sure. But this researcher decided to keep it dummy variable throughout. That's your choice, but you have to rationalize that choice in your writing, which is fine, but you have to do that. You have to provide explanations for everything that you do in research, okay? We don't just do it and then just, we have to make sense of why we do it. So a study must have at least 1 dependent variable. We've talked about dependent variable before. When we introduced relationships in lecture 3, we talked about it. And so our dependent variable hopefully would be based on the 3. The only one I could think of it would be death penalty. What is your main question? Your main question is, what does death penalty what affects people's opinions, right, about the death penalty? Might gender do it? Do men think differently than women when it comes to this opinion? What about education? The more or less education you have, does that affect your opinion about death penalty, right? So we state our research hypotheses and our null hypotheses. So for our our null hypothesis, we would say there is no relationship in the population between gender and the death penalty. There's no relationship, right? What would be another null hypothesis? Well, we have another independent variable, so it would be there is no relationship in the population between education and the death penalty. But again, these are things that we only understand in theory, but we never, ever, ever will we ever see this written out in any research paper. The null hypothesis is a theoretical. There is no relationship in order to use our decision rules. It has nothing to do with when you're writing, okay? A generic research hypothesis for our two relationships between gender and opinion, education and opinion, right? So we should have two hypotheses. The first research hypothesis, there is a relationship between gender and death penalty. And the second, there is a relationship between education and death penalty. Now that's just I think that's what I want to do my study on. And so I think that that's where I'm going to see a relationship there. I call it generic because that most people in most studies, you'll see a more specified research hypothesis where they've actually gone out and done and read some literature that might indicate why they might think maybe that males would favor more than females, or maybe that females would favor more than males, right? Or maybe that more educated people would favor more than less educated people, right? You have to actually go and do a literature review to allow you to be more specific about your research hypothesis. And it's this third set, right? This third set of hypotheses, this specific research hypotheses, this is what you see in a research paper. Not a null hypothesis, not a generic hypothesis, but a specified research hypothesis that says some direction. Males will favor more than females. More educated will favor more than less educated people. And hopefully this also sounds like the same lingo that we just learned in lecture 4 with correlation coefficients, right? Our correlation coefficients show us a number and we're able to say the more the this, the more the that, right? The more educated you are, the more likely you are to have favor the death penalty, right? The more educated you are, the higher your salary. Or for the dummy variable, males will favor more than females. Males would have higher salaries than females, right? So if we remember lecture 4, this is the same terms. So once you learn this term once, you never have to learn another thing. It's the same terms. It's the same lingo, okay? So the point of this slide is to show you how you could go from a thought of, I wonder what causes one's opinions about their penalty to vary, right? Would it be gender? Would it be education? All right, well, let's go do a research, literature review, right? Let's go look through the literature and let's see what what specific hypothesis we would come to. Okay. And let me just say also that the literature review that tells you something like men would favor more than females, if you actually find that a study has already done that, then guess what? You're not going to be paid to do that study unless there's some nuanced reason, some additional thing that you're adding to that study. There's no other reason to do that paper if the answer is already out there. So if the answer is out there, why would you even do the study? Why would someone pay you to do that study if it's already out there? So more than likely, if you're doing a study, right, the answers are not already out there. And so say, for example, we have no idea what causes death penalty opinions to change. We do today, But say the very first person who wanted to look that up was curious, and so they thought, gosh, I can't find that exact answer, but in order to come up with a specified research hypothesis, how about I look at how men and women, their psyche, is one more giving or is one more nurturing? Maybe since females might be more nurturing, maybe that means that they might be less likely to favor than men. Or maybe the more educated you are, the more snooty you become, and so maybe they're like, yeah, throw them all in prison and then annihilate them, right? So maybe there's something about education that leads one to being more harsh on crime. I don't know, right? But these are the ways that this is the literature you would be reading to find out how you would pose this final specified research hypothesis. Okay, I rest my case. Let's move on to our, I think, last slide. So our last slide here, some caveats about hypothesis testing. I'm going to give two really basic examples that people can probably relate to, because it's a court case, right? And we'll say our null hypothesis, someone's on trial, okay? That's a court case. Someone's on trial for murder. We'll say that our null hypothesis is that the person on trial is not a murderer, okay? Because based on the premise that in the US, people are considered innocent unless proven otherwise. I won't touch on that. And then our research hypothesis, the reason why we are in this courtroom is because the person on trial is a murderer, and we're going to prove that. So before the trial begins, the judge, the jury, everybody already believes that the defendant is guilty. A lot of times we know that that is what we see in our justice system, but we go on trial and hope for the best. So our research hypothesis, no relationship between this person and this murder. No relationship between this person and murder, right? Because that's what our null hypothesis means, none, right? Research hypothesis, there is a relationship between this person and the murderer. And the murderer. This person is the murderer. All right, not funny, but so with that scenario, let's look at the two caveats of hypothesis testing. There are two types of errors. The first type is type 1. If a jury convicts a truly innocent person, that's a type 1 error. So incorrectly rejecting the null hypothesis. Rejecting the null hypothesis even though it is true. What does that mean? Okay, that means that we said we were 95% confident, and that means there was a 3% probability of error. That 3% probability of error, there is a possibility that even though we said, oh, we reject the null, and we have now found this person guilty, right? There is a relationship between this person and the murder, so we reject the null and we find this person guilty. Okay, that means that 5% probability of error is that, well, we found this person guilty, but there's a possibility that this person is actually innocent. We just rejected the null that the person is not a murderer. But in fact, and we've seen this, right, in real life, we've actually seen cases like this where the person comes back and we find out, oh my God, you spent 25 years in prison, and now we have DNA testing that shows you weren't the person. You weren't even at the scene of the crime. That is a type 1 error. Ladies and gentlemen, type 1 error, where sadly, you are 95% confident. The jury just knew that person is guilty. That 5%, that little 3%, you were 97% confident, and then that 3%, boom, gotcha. And you were wrong, because you still have a chance of being wrong, and there you go, you were wrong, right? A key step in hypothesis testing is deciding how willing you are to make a type 1 error. This we call, I've said it before, but we'll say it again, our significance level. Our p-value is a significance level. So how confident are we willing to be, right? That's the opposite of our significance level, our probability of error. Okay, so we can actually control for that. But here's type 2 error. Type 2 error is if we incorrectly accept the null hypothesis. So we say this person, we accept the null, right? The null is a person on trial is not a murderer. So if we incorrectly accept the null, we're saying that a truly guilty person, we just set free. Not funny, still not funny. I just laugh a lot. So we incorrectly accept the null. So the jury fails to reject the null hypothesis, even though the null hypothesis is false. This person does have something to do with this murder. This person is the murderer. But we tentatively accepted the null, and we said this person has nothing to do with the murder. Now, this type 2 error is almost always unknown. We, as researchers, have no way of determining this number. We don't know. Increasing the sample size decreases our chances of making a type 1 error. Let's stop there in that sentence. What does that mean? Because we're looking at a sample, right? A sample is a subset of the population. So if we increase our sample, we get closer to the size of that population. And so that makes it less likely that we're going to have this error, that what we're saying about the sample and generalizing to the population would be true, or would be wrong. That decreases our chances of error, right? But as we do that, and there's a big but it also increases our chances of making a type 1 error. It actually, type 2 error. So as we decrease our type 1 error by increasing sample size, we're increasing type 2 error, and we have no way of controlling that. That type 2 error, both errors are very bad, very bad. Whether you put someone in prison incorrectly, an innocent person in prison, or you allow in a type 2 error, can also be equally as problematic, because now a killer is back on the loose. That's tough. That's tough. Which one is are you more willing to accept? Well, one you can actually control, right? We can actually control that one type 1 error. Type 2 error, completely unknown. So it's just important for you to understand the caveats behind hypothesis testing, and that even though we're saying, oh, I'm 99.9% confident, that 0.001 could be, 25 years later, we find out, oh man, this medicine we've been giving you, it doesn't cure cancer, or it actually increases high blood pressure, or, right? Don't get me started with pharmaceuticals, but these probabilities, we find out later, oh man, that percent of error was, even as small as it was a huge deal. And now it's causing people to die off, or it's causing, I might not have cancer anymore, but now I got a whole slew of other things I got to deal with, right? So that's all for today. Lecture 5. Go get ready for your quiz, do your homework and your practice, and we'll do a review the next time I see you. Bye-bye.